what's a good example? Like blackbody radiation in the 1860s with Gustav Kirchhoff. It should have produced this ultraviolet catastrophe, and it didn't. And it was because of, quanta, which Planck discovered 40 years later.
Bonjour tout le monde. Today's video is going to begin a partial review of Quantum Theory by David Bohm. This is a special book because Bohm est l'amant de guerre donné à l'interprétation de la théorie quantique par les hidden variables. But in this book, as will be discussed here, Bohm develops the so-called Copenhagen interpretation a la Bohr and Heisenberg. And in this text, Bohm is actually critical of hidden variables. Like other physics books, a mathematician might say it's loosey-goosey in its math treatment. That's a term of art, loosey-goosey. However, the book is unique in its philosophical perspective, and its place in time makes it an interesting touchstone in the development towards the current understanding. The book has 6 parts, which develop quantum theory not only through mathematical, abstract, theoretical arguments, but closely along experimental lines. Quantum Theory by David Bohm was originally published in 1951, that is to say before the dumpster fire known as the Standard Model of particle physics raged into the inferno it is today. Extreme amounts of money had not yet been spent to build massive particle colliders in multinational efforts, and thus only the OG quantum experiments form the foundation of Bohm's presentation in the book. To further understand what this means, it is worth briefly reviewing first the state of physics leading up to Bohm's book, as this is referred to as classical physics throughout the text. Physics at the time of Bohm's writing in the early 1950s had already made tremendous relative progress in the understanding of mechanics, electromagnetism, thermodynamics, fluid dynamics, and optics. The giants include Isaac Newton and James Clerk Maxwell, but a few other special mentions are worth making for the purposes here. Christiaan Huygens, the inventor of pendulum clocks, was a contemporary of Descartes and Fermat, and would anticipate calculus by about a decade in his geometric studies. Huygens authored the first modern work on mechanics, Horologium Oscillatorium, which idealizes a physical problem by analyzing a set of mathematical parameters. Huygens would also inaugurate the wave theory of light. However, this was overshadowed by Newton's corpuscular theory of light. Newton is obviously a physics giant, and still to this day, although Leibniz notation is the norm, physics problems often amount to posing and analyzing or solving a differential equation or system of differential equations using calculus. In the wake of Newton, this sort of general mathematical approach helped motivate the rigorous development of the branch of mathematical analysis. Figures such as Siméon, Denis, Poisson would develop mathematical formulations from physical ideas that would turn out to be incorrect, but the math would be vindicated. Augustin-Jean Fresnel and Augustin-Louis Cauchy would independently refine math and physics to a point where a wave theory of light would result, thus supplanting Newton's corpuscular theory of light. Figures such as Karl Weierstrass would formalize mathematical analysis to give calculus the rigorous underpinning necessary to make increasingly precise statements in applications including physics. Weierstrass's rigor enables the modern treatment of expressions such as Poisson's equation, or the system of differential equations governing electromagnetism named after the giant in his own right, James Clerk Maxwell, Maxwell's equations. In the scope of Bohm's quantum theory, thermodynamics around Maxwell's time is worth exploring briefly before getting into the book. Before Maxwell came Otto von Guericke, who in 1650 was motivated to disprove Aristotle's supposition that nature abhors a vacuum, and so he built the first known vacuum pump and demonstrated a vacuum, thus inaugurating modern thermodynamics. Thermodynamics would culminate in the analysis of processes and systems in terms of their energy, entropy, volume, temperature, and pressure, and would be tangential to a deeper understanding of the nature of atoms and molecules. Democritus's atomism would begin to be rigorously empirically validated around the turn of the 19th century through the findings of Joseph Priest and John Dalton in chemistry, which provided evidence that chemical elements combine with each other by basic units of weight. Critically, by the late 19th century, the reality of atoms and molecules was still disputed by philosophers and scientists alike, opposed to the descriptions made by Maxwell, for example, as made in his paper Illustrations of the Dynamical Theory of Gases, and the overall kinetic theory of gases, including the second law of thermodynamics developed by Boltzmann. Recall that thermodynamics in this era would originate two iconic philosophical thought experiments, namely Boltzmann brains and Maxwell's demon. Both are related to a contemplation of the concept of entropy and the second law of thermodynamics, which states that the entropy of an isolated system left to spontaneous evolution cannot decrease with time. Max Planck, who will be discussed further shortly, once stated that the logarithmic connection between entropy and probability was first stated by Ludwig Boltzmann in his kinetic theory of gases. Entropy and the second law of thermodynamics are pillars of Boltzmann's statistical mechanics in their description of how macroscopic observations such as temperature and pressure are related to microscopic parameters that are described probabilistically. A Boltzmann brain is the idea that it is probably more likely for a brain to spontaneously form, complete with a memory of having existed in the universe, rather than for the entire universe to come about in the manner cosmologists think it actually did. Maxwell's demon directly confronts the second law of thermodynamics by aiming to directly disprove it. Maxwell's demon controls a door between two chambers filled with gas, and as the individual gas particles approach the door, Maxwell's demon quickly opens and closes the door so as to only allow fast-moving particles in one chamber and only allow slow-moving particles into the other. This would lead to the kinetic temperature of one chamber to warm up and the other to cool down due to the actions of Maxwell's demon, therefore decreasing the total entropy of the system seemingly without applying any work, and thus violating the second law of thermodynamics. Although the text is by no means organized in a strictly historical order, the discourse on physics presented in Bohm's book Quantum Theory begins with advances made around the turn of the 20th century. A major motivation for developing a deeper understanding of physics, namely thermodynamics, at the border of macroscopic and microscopic phenomena in this time, was the improvement of steam engine efficiency, which was part of the main thrust of the ongoing Industrial Revolution. Lord Kelvin was a player at the heart of the engine room of this drive towards greater thermodynamic understanding. In a lecture he gave towards the end of his heyday in 1900, Lord Kelvin pronounced that two, quote, dark clouds, unquote, loomed over physics at the time, specifically confusion from one, the results of the Michelson-Morley experiment concerning how matter moves through the ether, and two, black body radiation. The fog of these clouds would lift to shed light on what are now pillars of modern physics, relativity and quantum theory. The story goes that the foundation of modern physics in general is built upon the emergence of these fields, and Einstein's four 1905 Annus Mirabilis papers. Each of these papers respectively covered the photoelectric effect, Brownian motion, special relativity, and mass energy equivalence, all of which will be conceptually in the background of Bohm's quantum theory to various extents. Everyone is now an expert in relativity and fluent in differential geometry, but appreciating the origins of quantum theory and the beginnings of Bohm's book involves exploring the problem of Lord Kelvin's second cloud, which led to the so-called, quote, other pillar, unquote, of modern physics, namely black body radiation. The story of the exploration of black body radiation is intertwined with the story of the exploration of the specific heat of a substance. The common theme of these two explorations is the concept of thermal energy equilibrium. Keep in mind that thermal equilibrium occurs when there is no net flow of thermal energy between connected systems, whereby the temperature is uniform and heat is not being exchanged. Thermodynamic equilibrium is broader and requires that simultaneously there is thermal equilibrium, mechanical equilibrium, namely no pressure differences, and chemical equilibrium. Black body radiation is the thermal electromagnetic radiation in thermodynamic equilibrium within a black body. A black body in Bohm's context is an idealized, perfectly insulated hollow cavity. The original radiant energy within the black body continually emits waves of every possible frequency and direction at a rate which increases very rapidly with the temperature. But this emission is opposed by the process of absorption in the walls taking place at a rate proportional to the intensity of radiation already present in the cavity. Thus, the black body and its internal radiation are in thermodynamic equilibrium. To observe or measure this internal radiation, a hole is made in the wall of the black body which is effectively small enough that there is a negligible effect upon the system's equilibrium. The idea of a black body goes back to Newton, who stated in his work titled Optics that do not black bodies conceive heat more easily from light than those of other colors do, by reason that the light falling on them is not reflected outwards, but enters into the bodies, and is often reflected and refracted within them until it be stifled and lost. Augustin-Jean Fresnel would later respond by saying that a black body under illumination would increase indefinitely in heat. This sort of back and forth is a debate surrounding the relationship between the energy and wavelength of electromagnetic radiation and or light incident upon matter, the energy absorbed by the matter, if any, and the energy and wavelength of the electromagnetic radiation and or light subsequently emitted by the matter as a result. To assess the validity of such purported truths and the extent that they apply in nature, theoretical and experimental approaches were taken. Begin with the system of partial differential equations that are Maxwell's equations, namely Gauss's law for magnetism, Faraday's law, and the Ampere-Maxwell law. The black body cavity contains energy in the form of electromagnetic radiation, so determine the energy distribution among the frequencies in the cavity when the walls are at a given temperature. The periodic nature of these waves in terms of the contributions of various frequencies lends itself to a solution via the series expansion in terms of orthogonal functions, that is, a Fourier analysis. Thus, the radiation behaves like a collection of simple harmonic oscillators called, quote, radiation oscillators, unquote, which can be given a classic statistical mechanical treatment that yields the mean energy of each oscillator at equilibrium with the black body walls at a temperature capital T. This enables the determination of the number of oscillators in a given frequency, which when multiplied by the mean oscillator energy yields a thermodynamic result known as the Rayleigh-Jeans Law. General electric and magnetic fields are given through Maxwell's equations in terms of vector and scalar potentials, say, lowercase a and phi. Namely, in Bohm's notation, the magnetic field H is equal to the curl of A, and the electric field is equal to negative 1 over c times the partial derivative with respect to t of A minus the gradient of phi. These solutions of Maxwell's equations are not unique, and so an arbitrary scaling which maps A and phi to A prime and phi prime can be introduced that leaves the magnetic field H and the electric field E unchanged. These scalings are the gradient of psi subtracted from the vector potential A, since this leaves the magnetic field H unchanged, that is, the curl of the gradient of psi is equal to 0, and 1 over c times the partial derivative with respect to t of psi added to the scalar potential phi, since this leaves the electric field E unchanged. Thus, one has that A prime equals A minus the gradient of psi, and phi prime is equal to phi plus 1 over c times the partial derivative with respect to t of psi. Additionally, imposing the condition that the divergence of A is equal to 0 completes making a transformation called the Coulomb gauge fixing. The Coulomb gauge, also known as the transversive radiation gauge, is a gauge fixing condition specifically defined by the setting of the divergence of the vector potential to 0. This is useful in non-relativistic quantum electrodynamics and for bound or stationary states, in that it eliminates non-physical degrees of freedom, allowing for a natural Hamiltonian formulation and instantaneous longitudinal interactions. Recall that the Hamiltonian of a system refers to an operator corresponding to the total energy of that system, namely the combined kinetic energy and potential energy, denoted as capital H hat equals capital T hat plus capital V hat. This gauge fixing condition is thus sometimes referred to as the transverse gauge because it ensures that the vector potential is purely transverse. In quantum electrodynamics, eliminating non-physical degrees of freedom amounts to isolating physical photons, namely their transverse components, and furthermore, the Coulomb gauge separates the longitudinal Coulomb potential from the radiation field. The advantage is that this directly shows the electrostatic potential or the static Coulomb interaction as the scalar potential, but the disadvantage is that it is not a relativistic gauge fixing condition such as the Lorentz gauge, that is, the divergence of A plus 1 over c squared times the partial derivative with respect to t of capital V is equal to 0, which is Lorentz invariant. After imposing the Coulomb gauge condition that the divergence of A is equal to 0, the invariance of fields serves the purpose of simplifying the previously obtained scaled expressions for the electric and magnetic fields. This requires calculating a new expression for the divergence of A prime, or, in other words, psi must be chosen so that the divergence of A minus the Laplacian of psi is equal to 0. Recognize that what is being sought is the solution of Poisson's equation. Psi is thus the solution of the potential field in Poisson's equation from the source density given by the divergence of A prime. The general representation of this solution is given by psi equals -1/4 pi times the triple integral of a fraction with a numerator of the divergence of A in terms of x prime, y prime, z prime, and t, dx prime, dy prime, dz prime, all over a denominator of the magnitude of r minus r prime. The formulation of this general representation demonstrates that a Coulomb gauge transformation that yields the divergence of A prime can always be calculated. The physical formulation of the problem can be followed to further simplify the previous general expressions for the electric and magnetic fields. The black body cavity by hypothesis does not contain any charges and is therefore empty space. The choice that the divergence of A is equal to 0 also leads to phi being equal to 0. This can be seen by substituting the electric field equal to -1/c times the partial derivative with respect to t of A minus the gradient of phi into Gauss's law. Namely, we have that the divergence of the electric field is equal to -1/c times the divergence of the partial derivative with respect to t of A minus the Laplacian of phi is equal to 0. Then, the divergence of A being equal to 0 implies that the Laplacian of phi is equal to 0. And this is obviously Laplace's equation. Therefore, an analytic deduction by the regularity of Laplace's equation from its algebraic structure indicates that the only solution of this equation over all of space is phi equals 0. Otherwise, non-zero regular solutions could only occur provided that the charge density ρ is not everywhere 0, and thus relevant solutions of Poisson's equations would be sought. Therefore, the electric and magnetic field expressions subject to the divergence of A in the absence of charges are given by the magnetic field is equal to the curl of A, and the electric field is equal to -1/c times the partial derivative with respect to t of A. The physical formulation of the black body cavity additionally hypothesizes 0 charge density therein, so substituting the foregoing expressions for the electric and magnetic fields into the Ampere-Maxwell law obtains the partial differential equation, the Laplacian of A minus 1/c squared times the second order partial derivative with respect to t of A is equal to 0. The next step is to specify the boundary conditions to obtain an appropriate solution for this partial differential equation. The theoretical black body cavity can be idealized by first considering a cube of side length capital L with very thin, non-conductive walls repeated periodically through the space in all directions, and thereby the radiation fields are the same at corresponding points of every internal cube. These idealized walls being thin and non-conductive serves to prevent the system from gaining or losing energy. This motivates seeking a solution in terms of periodic fields, which achieves the same effect as such theoretical very thin non-conductive walls because each cube can't gain nor lose energy from the other cubes, and thus the energy in any single cube is constant. This motivates seeking a solution in terms of periodic fields, which achieves the same effect as such theoretical very thin non-conductive walls because each cube can't gain nor lose energy from the other cubes, and thus the energy in any single cube is constant. Since the walls of the black body cavity are absorbing and emitting radiation in thermodynamic equilibrium, the sole restriction imposed on Maxwell's equations in this situation is that the solution A in terms of x, y, z, and t is periodic in space with a period capital L over lowercase n, where lowercase n is an integer. This scenario lends itself to employing a Fourier analysis where a partial differential equation is transformed into an ordinary differential equation or an algebraic equation with fewer variables. Furthermore, the expansion of the solution in terms of the basis of orthogonal functions such as sines and cosines is conducive to representing periodic solutions. In the context of black body radiation, an arbitrary function f is sought here as a sum of standing waves of all possible wavelengths and magnitudes. There are a handful of various ways of expressing a Fourier series, but the representation given in Bohm's quantum theory is to write the function f as f in terms of x, y, z, and t is equal to the sum over lowercase l, m, and n of coefficient a in terms of lowercase l, m, and n of t times the cosine of 2 pi over capital L, then times the quantity lowercase l times x plus m times y plus n times x plus quantity plus the coefficient b in terms of lowercase l, m, and n of t, then times the sine of 2 pi over capital L, then times the quantity lowercase l times x plus m times y plus n times z, close all quantities, for the integers lowercase l, m, and n from negative infinity to infinity, including 0. Convergent a and b coefficients thus define a periodic function f. These coefficients were expressed in Bohm's book through the relations coefficient a in terms of lowercase l, m, and n of t plus coefficient a in terms of lowercase negative l, negative n, and negative n of t is equal to 1 over capital L cubed times the triple integral where each integral is from 0 to capital L respectively of dx, dy, dz times the cosine of 2 pi over capital L times the quantity lowercase l times x plus m times y plus n times z close quantity times f in terms of x, y, z, and t, and coefficient b in terms of lowercase l, m, and n of t minus coefficient b in terms of lowercase negative l, negative m, and negative n of t is equal to 1 over capital L cubed times the triple integral, each integral from 0 to capital L respectively, of dx, dy, dz times the sine of 2 pi over capital L times the quantity lowercase l times x plus m times y plus n times z close quantity times the function f in terms of x, y, z, and t. And as such, f is specified only by the coefficients a in terms of lowercase l, m, and n, and the coefficients b in terms of lowercase l, m, and n. Notably, this involves the following orthogonality relations, namely the triple integral, each integral from 0 to capital L respectively, of dx, dy, dz times cosine of 2 pi over capital L, then times the quantity lowercase l times x plus m times y plus n times z close quantity, then times the sine of 2 pi over capital L, then times the quantity lowercase l prime times x plus m prime times y plus n prime times z close quantity equals 0, and the triple integral, each integral from 0 to capital L respectively, of dx, dy, dz times the cosine of 2 pi over capital L, then times the quantity lowercase l times x plus m times y plus n times z close quantity, then times the cosine of 2 pi over capital L, then times the quantity lowercase l prime times x plus m prime times y plus n prime times z close quantity equals 0, which hold unless lowercase l equals lowercase l prime, m equals m prime, and n equals n prime, or lowercase l equals negative l prime, m equals negative m prime, and n equals negative n prime, and therefore each coordinate equals capital L cubed over 2, or otherwise, when lowercase l equals n equals n equals 0, then each coordinate therefore equals capital L cubed. Similarly, the triple integral, where each integral is from 0 to capital L respectively, of dx, dy, dz times the sine of 2 pi over capital L, then times the quantity lowercase l times x plus m times y plus n times z close quantity times the sine of 2 pi over capital L, then times the quantity lowercase l prime times x plus m prime times y plus n prime times z close quantity equals 0, which is subject to the same caveat as previously for the coordinates lowercase l, m, and n for the other orthogonality relations. Using these expressions and relations, the vector potential can now be expanded in a Fourier series. Since the solution A has been formulated as a vector with 3 components, the Fourier coefficients A in terms of lowercase l, m, and n, and B in terms of lowercase l, m, and n likewise have 3 components. Thus, we have that A equals the sum over lowercase l, m, and n of coefficient A in terms of lowercase l, m, and n of t, then times the cosine of 2 pi over capital L, then times the quantity lowercase l times x plus m times y plus n times z close quantity plus the coefficient B in terms of lowercase l, m, and n, then times the sine of 2 pi over capital L times the quantity lowercase l times x plus m times y plus n times z close all quantities. And here we assume that the offset A at lowercase l being equals 0, m being equals 0, and n equals 0 is equal to 0. At this point, Bohm defines a propagation vector, lowercase k, via k sub x is equal to a fraction with the numerator of 2 pi times lowercase l over a denominator of capital L. Similarly, k sub y is equal to a fraction of 2 pi times m over capital L. K sub z is equal to a fraction with the numerator of 2 pi times n over capital L. And k squared is equal to the quantity 2 pi over capital L close quantity squared, then times the quantity L squared plus n squared close quantity. Next, the coordinate axis is oriented so that the z-axis is along k. Thus, lowercase l equals m equals 0 and k equals 2 pi over capital L. The definition of k implies that k over the denominator of 2 pi is the number of waves in the distance capital L. In other words, the wavelength is lambda equals 2 pi over k, which is equivalent to saying that k equals 2 pi over lambda, which implies that k is in the direction that the phase of the wave changes. Changing back to arbitrary coordinate axes implies that the vector k is in the direction of the wave's propagation magnitude. That is, 2 pi over lambda, and is allowed to take on the values permitted by integral values of lowercase l, n, and n per the previous definitions. Accumulating these results and simplifying the notation yields a equals the sum over k of coefficient a sub k in terms of t, then times the cosine of the dot product of vector k with vector r, then plus the coefficient b sub k, then times the sine of the dot product of vector k with vector r, where the sum is over all permissible values of k. Applying the divergence of a being equal to 0 to this statement yields that a is equal to the sum over k of negative of the dot product of the vector k with the coefficient a sub k, then times the sine of the dot product of the vector k with the vector r, then plus the dot product of the vector k with the coefficient b sub k, then times the cosine of the dot product of the vector k with the vector r, and this is all equal to 0. By the previous orthogonality relation, if a Fourier series sums to 0, then all coefficients a sub k and b sub k must vanish. Therefore, the dot product of the vector k with the coefficient vector a sub k in terms of t is equal to the dot product of the vector k with the coefficient vector b sub k, both being equal to 0. And this coefficient vector a sub k and coefficient vector b sub k are orthogonal to the vector k, as are the electric and magnetic fields of the kth wave. Vibrations are also normal to the propagation direction, and therefore the waves are transverse. The direction of the electric field is referred to as the direction of polarization. We turn to the coordinate axes where the z-axis is in the direction of the vector k to describe the orientation of the coefficient vector a sub k. A sub k only has x and y components. Therefore, specifying these also specifies the magnitude and direction of the vector a sub k. Thus, designate the direction of vector a sub k by the polarization index mu and write vector a sub k mu such that mu equals 1 or 2. That is, mu being equal to 1 designates the x direction, and mu being equal to 2 designates the y direction. All possible a sub k vectors can be represented as the sum of some a sub k1 and a sub k2. Therefore, the most general vector potential subject to the initial condition that the divergence of A is equal to 0 is given by vector A in terms of vector R, and T is equal to the sum over K and mu of coefficient vector A sub K mu in terms of T, then times the cosine of the dot product of vector K with vector R, dot product with the coefficient vector B sub K mu in terms of T, times the sine of the dot product of vector K with vector R, close sum, then times the unit vector epsilon sub k mu, or epsilon hat sub k mu, where epsilon hat sub k mu is perpendicular to the vector k such that each mode, vector A sub k mu, satisfies that the second order derivative with respect to t of vector A sub k mu, then plus k squared times c squared times vector A sub k mu is equal to 0. Note that this equivalently amounts to stating that the vector A sub k mu terms oscillate with simple harmonic motion with an angular frequency omega equals c times the magnitude of the vector k, which follows from the wave equation for the vector A. The next step is to evaluate the electromagnetic energy in the volume of the black body cavity. The total energy in the matterless space due to the radiation is given by energy capital E is equal to 1 over 8 pi times the integral of the square of the electric field plus the square of the magnetic field d tau. This follows from the Poynting theorem, which states that the rate of energy transfer per unit volume from a region in space equals the rate of work done on the charge distribution in the region plus the energy flux leaving that region. Recall that the goal is to determine the energy distribution among the frequencies in the cavity when the walls of the black body are at a given temperature. Thus, the previous expression for the total energy in the cavity will be evaluated over a cube of side length capital L using the foregoing Fourier series result for the vector A. First, the electric field is given by E equals negative 1 over C times the sum over K and mu of A dot sub K mu times the cosine of the dot product of vector K with vector R plus B dot sub K mu times the sine of the dot product of vector K with vector R, where the fly dot notation indicates the derivative with respect to time. Next, the magnetic field is given by H equals the sum over K and mu of the cross product of negative K with A sub K mu, then times the sine of the dot product of vector K with vector R, then plus the cross product of vector K with vector B sub K mu, then times the cosine of the dot product of vector K with vector R. Next, evaluating the expression for electromagnetic energy over a cube of side length capital L yields 1 over 8 pi times the integral of the square of the electric field d tau equals 1 over a denominator of 8 pi times c squared, then times the double sum, where the first sum is over k mu, the second sum is over k prime and u prime, then times the triple integral, where each respective integral is from 0 to capital L of dx dy dz times the entire quantity A dot sub k mu dot product with A dot sub k prime mu prime, then times the cosine of the dot product of vector k with vector r, then dot product with the cosine of the dot product of vector k prime with vector r, plus the dot product of B dot sub k mu with B dot sub k prime mu prime times the sine of the dot product of k with r, then dot product with the sine of the dot product of k prime with r, plus the dot product of A dot sub k mu with B dot sub k prime mu prime, then times the cosine of the dot product of k with r, then dot product with the sine of the dot product of k prime with r, plus B dot sub k mu dot product with A dot sub k prime mu prime times the sine of the dot product of k with r, then dot product with the cosine of the dot product of k prime with r. All integrals vanish except when the vector k is equal to the vector k prime, and all terms involving the dot product of A dot sub k mu with B dot sub k mu prime are equal to 0. Also, the dot product of A dot sub k mu with A dot sub k mu prime is equal to 0 unless mu equals mu prime. Next, the statement for electromagnetic energy reduces to the integral of the electric field squared d tau all over a denominator of 8 pi, which is equal to a fraction with a numerator of capital L cubed over a denominator of 8 pi c squared times the sum over k and mu of 1/2 times the square of A dot sub k mu plus 1/2 times the square of B dot sub k mu, and similarly, the integral of the square of the magnetic field d tau over 8 pi equals a fraction with a numerator of capital L cubed over a denominator of 8 pi times the sum over k and mu of k squared times 1/2 the square of A sub k mu plus 1/2 times the square of B sub k mu. Therefore, the electromagnetic energy in the cavity where capital L3 is denoted as capital V is thus: electromagnetic energy equals a fraction with a numerator of capital V over a denominator of 8 pi c squared times the sum over k and mu of 1/2 times the quantity A dot sub k mu squared plus c squared times k squared times the square of A sub k mu, close quantity, then plus 1/2 times the quantity square of B dot sub k mu plus c squared k squared times the square of B sub k mu, close all quantities. Two observations follow. First, this previous statement is a sum of separate A sub k mu and B sub k mu terms. Therefore, different wavelengths and polarizations don't interact. The energy of each propagation vector k and polarization direction mu is proportional only to the square of A dot sub k mu and A sub k mu, and likewise for the B coefficients. Second, the energy of the A and B coefficients respectively has the same mathematical form of a simple harmonic oscillator, that is, a simple harmonic oscillator with effective mass m and angular frequency omega, and has the energy capital E equals m over 2 times the quantity x dot squared plus omega squared times x squared closed quantity, and the effective mass given by m equals a fraction with the numerator capital V over a denominator of 8 pi times c squared, and likewise angular frequency omega equals k times c. Therefore, the frequency denoted lowercase f equals omega over 2 pi is equal to k times c over 2 pi, which is equal to c over lambda, which is the same as an electromagnetic wave with wavelength lambda. Also, from the expression of momentum for a simple harmonic oscillator P equals m times x dot, that in the present context of the blackbody radiation solution, it follows that P dot sub k mu is equal to a fraction with a numerator of capital V over a denominator of 8 pi times c squared, then times a dot sub k mu. Thus, the expression for the Hamiltonian of a simple harmonic oscillator, capital H equals P squared over 2m plus a fraction with a numerator of m times omega squared times x squared all over a denominator of 2, implies that in the present context, the Hamiltonian is given by capital H equals a fraction with a numerator of 8 pi times c squared over a denominator of capital L cubed, then times a fraction with a numerator of the square of P dot sub k mu over a denominator of 2, then plus a fraction with a numerator of capital L cubed over 8 pi, then times k squared, then times a fraction with the numerator of the square of a sub k mu all over a denominator of 2, and likewise for b sub k mu. The correct equations of motion are obtained from the Hamiltonian. A dot sub k mu equals partial h partial p sub k mu, and p dot sub k mu is equal to negative partial h partial a sub k mu. This yields the previous expression, which was originally obtained by direct substitution into Maxwell's equations. Therefore, a double dot sub k mu plus c squared times k squared times a sub k mu equals 0, and similarly for the b coefficients. A sub k mu and b sub k mu are thus analogous to the coordinates of separate non-interacting harmonic oscillators, and also may be regarded as the coordinates of the radiation field. There exist as such a countable infinite number of coordinates via the possible values of k. The previously calculated Fourier series describes fields in continuous space via a discrete infinite number of coordinates. For each k, there are then two independent coordinates, namely a sub k mu plus a sub negative k mu and b sub k mu minus b sub negative k mu. The next step is to find the number of oscillators with frequencies between v and v plus dv. Since v equals kc over 2 pi, this is equivalent to finding the number of oscillators between k and k plus dk. Choose dk to be so small that no important physical quantity such as mean energy, for example, changes appreciably, but so large that very many radiation oscillators are included. This choice is made because many so-called reasonable choices of k would enable a large number of waves inside the box. By choosing dk in this way, the number of oscillators can be treated as virtually continuous and may be represented via a density function. The task is thus to find the number of oscillators in the volume dk sub x, dk sub y, and dk sub z. But there is one oscillator per unit cube of lowercase l and n space implies that the density in this space is 1, or unity. The previous definitions for the propagation vector are then used to transform to k-space, therefore writing delta capital N sub 1 equals d lowercase l times dm times d lowercase n, which is equal to dk sub x, dk sub y, dk sub z. Next, adopt polar coordinates so that k squared equal to k sub x squared plus k sub y squared plus k sub z squared transforms the element of volume as k squared dk d capital omega, where d capital omega is the element of solid angle. Integrating over d capital omega leads to a new element of volume 4 pi k squared dk, and therefore delta capital N sub 1 is equal to a fraction with the numerator of 4 pi capital V over a denominator of the cube of 2 pi, then times k cubed dk. By writing V equals kc over 2 pi, the expression delta capital N sub 1 is equal to 4 pi times capital V times a fraction with the numerator of lowercase v squared d lowercase v over a denominator of c cubed is obtained, which gives the number of permissible values of k in the range lowercase v to lowercase v plus d lowercase v. Recall that there are two independent coordinates for all k, namely the a and b coordinates, and commensurately two directions of polarization. Therefore, the number of oscillators between lowercase v and lowercase v plus d lowercase v is finally given by delta capital N equals 2 times delta capital N sub 1 equals a fraction with a numerator of 8 pi times capital V over a denominator of c cubed, then times lowercase v squared d lowercase v. The final step in the derivation is to apply classical statistical mechanics to calculate the mean energy possessed by each oscillator at thermodynamic equilibrium with the black-body walls. Such a treatment applies to all systems acting like material oscillators. In canonical ensemble, the probability, including a normalization factor capital A, that a system with total energy capital E, that is, both kinetic and potential energy, is in the phase space element dp/dq is given by capital A times e to the power of negative capital E over the quantity kappa times capital T close quantity dp/dq. But the requirement that is an expression of probability holds that the double integral of each integral, respectively from negative infinity to infinity, of capital A times e to the power of capital E over quantity kappa times capital T dp/dq is equal to 1. In the above, kappa denotes the Boltzmann constant, which is approximately 1.38 times 10 to the negative 23rd joules per Kelvin, which provides a proportionality factor between kinetic energy at the particle level to gaseous temperature. Next, the energy capital E must be specified. In the case of a perfect gas, energy would be given by capital E equals p squared over 2m, which leads to obtaining the Maxwell-Boltzmann distribution of velocities, capital A times e to the negative p squared over quantity 2m times capital T dp/dq. As here in the case for one harmonic oscillator, energy is rather given by capital E equals p squared over 2m, then plus m times omega squared times q squared over 2. Next, a change of variables is introduced. That is, lowercase p equals the square root of 2m, then times capital P, and lowercase q equals capital Q over omega, then times the square root of 2 over n, which yields that capital E is equal to capital P squared, then plus capital Q squared. Thus, the previous statement of total probability becomes 1 over capital A equals the double integral with each integral respectively over negative infinity to infinity of e to the power of negative capital E over kappa times capital T, then times 2 over omega d capital P d capital Q. The probability that the system lies within the phase space between capital P to capital P plus d capital P and capital Q to capital Q plus d capital Q is then dW in terms of capital P and capital Q is equal to a fraction with the numerator of e to the negative quantity capital P squared plus capital Q squared close quantity over kappa times capital T d capital P d capital Q over a denominator which is a double integral with each integral respectively from negative infinity to infinity of e to the negative quantity capital P squared plus capital Q squared close quantity over kappa times capital T d capital P d capital Q. Next, make another change of variables to transform the polar coordinates capital R and phi in phase space, where capital P squared plus capital Q squared equals capital R squared, which equals capital E, or capital R d capital R is equal to d capital E over 2. Solutions are sought in terms of capital R rather than phi. Thus, integration is taken over phi. Therefore, the normalized probability that the energy lies between capital E and capital E plus d capital E is given by capital E over bar equals a fraction with a numerator which is the integral from 0 to infinity of capital E times e to the power of negative capital E over kappa capital T d capital E over a denominator which is the integral from 0 to infinity of e to the negative capital E over kappa T d capital E, which is then equal to kappa times capital T times a fraction with the numerator of the integral from 0 to infinity of e to the negative epsilon, then times epsilon d epsilon over a denominator of the integral from 0 to infinity of e to the negative epsilon d epsilon, which is equal to kappa times capital T, where here epsilon denotes capital E over kappa times capital T. The foregoing demonstration that the average energy of each oscillator is kappa times capital T is an example of the equipartition theorem of energy. The theorem of equipartition of energy simply states that the total energy, both kinetic and potential, as critically per the case of harmonic oscillators, is shared equally among all of its independent parts on average once the system has reached thermal equilibrium. This is a more subtle statement than classic conservation of energy. Correcting the previous results yields what is known as the Rayleigh-Jeans Law, which is capital U of lowercase v d lowercase v is equal to capital E over bar times delta capital N, which is equal to the fraction with the numerator of 8 pi times capital V over the cube of C, then times kappa times capital T times lowercase v squared d lowercase v. Notice that this result is proportional to the square of frequency lowercase v squared. Large frequencies correspond to small wavelength, which in the case of electromagnetic radiation corresponds to the ultraviolet spectrum and above. Therefore, the Rayleigh-Jeans Law diverges towards infinity at increasingly high frequencies of radiation. This is problematic because the corresponding empirical evidence at the time had already demonstrated that, while the Rayleigh-Jeans Law agreed with experimental results at low frequencies, at high frequencies the emission reached a maximum and then fell with frequency, that is, the total energy emission is finite. This is referred to as the ultraviolet catastrophe.
It should have produced this ultraviolet catastrophe, and it didn't.
It indicates a shortcoming of the equipartition theorem from classical thermodynamics. A prevailing source of experimentally accessible black body radiation at the time of these developments in the years shortly before the turn of the 20th century was an exposed incandescent solid body serving as an approximation to black body radiation. The shortcoming of experimental approaches with such bodies is that they were mere approximations to the behavior of radiation in a theoretical black body. While perfect black bodies do not exist in nature, the departure of emitted radiation from an exposed incandescent solid body from the black body spectrum obscures the empirical discernment of the true black body spectrum. Nevertheless, experimental work by Otto, Fresnel, Bohm, Ernst Pringsheim, and Heinrich Rubens demonstrated a setup which led to progressively improved measurements approximating ideal blackbody radiation to more fully characterize the blackbody spectrum. Lumer and Bohm's design involved a platinum box divided by diaphragms and an interior black end with iron oxide, or later with a mixture of chromium, nickel, and cobalt oxides. With better experimental data, a notable improvement on describing blackbody radiation would be put forth by Wilhelm Wien. An abbreviated sketch of the derivation of Wien's approximation is as follows. It is assumed that the wavelength of the blackbody radiation is proportional to the square of its velocity. Begin with energy density rho in terms of lambda and capital T, which is equal to a function capital F of lambda times e to the negative a over lambda capital T, and then use the Stefan-Boltzmann law to obtain the integral from 0 to infinity of f of lambda times e to the negative a over lambda T d lambda is proportional to the fourth. Next, define y equals a over lambda t and write the expansion of f of lambda as f of lambda equals f of a over a denominator of y times t, which is equal to c sub 0 plus c sub 1 times y times t over a plus c sub 2 times y squared times t squared over a squared plus etc. plus c sub n times y to the n times t to the n over a to the n plus etc. plus c sub negative 1 times a over y times t plus c sub negative 2 times a squared over a denominator of y squared times t squared plus etc. plus c sub negative n times a to the n over y to the n times 2 to the n plus etc. Substituting this expansion into the integral resulting from the Stefan-Boltzmann law yields the integral from 0 to infinity of f of lambda then times e to the negative a over lambda times t d lambda equals a over t times the integral from 0 to infinity of f of a over y times t then times e to the negative y dy over y squared, which is equal to the sum over n of c sub n times t to the n minus 1 over a to the n minus 1 then times the integral from 0 to infinity of e to the negative y times y to the n minus 2 dy, which is equal to the sum over n of c sub n times t to the n minus 1 over a to the n minus 1, then times the gamma function at n minus 1. Since this is proportional to t to the fourth, coefficients c sub j for j greater than or equal to 5 must identically be 0, which yields f of lambda equals capital C over lambda to the fifth, where capital C is constant. Therefore, the energy density along the lines of the foregoing derivation has a form of rho in terms of lambda and t is equal to capital C over lambda to the fifth, then times e to the negative a over lambda times t. Choose capital C equal to 2 times h times c squared and a equal to h times c divided by kappa, where h is the Planck constant, c is the speed of light, and kappa is the Boltzmann constant. This distribution has a finite peak on a wavelength of lambda max equal to h times c over a denominator of 5 times kappa times t, which is approximately equal to 0.2878 centimeters times kelvins divided by capital T. However, the distribution as a whole still fails to accurately describe low-frequency radiation emission and does not provide a physical mechanism motivating its validity. The previous use of Planck's constant is retrospective and is merely arbitrary for fitting the relation to the empirical data. To adjust the high-frequency contributions to the ultraviolet catastrophe in the case of the Rayleigh-Jeans Law, Planck hypothesized that the energy of an oscillator of natural frequency V is restricted to integral multiples of the basic unit hV, that is, capital E equals nhv, where n is any integer from 0 to infinity. The discrete quantization implied by this hypothesis at first seems unphysical, since observations of macroscopic oscillators such as radio waves, pendulums, and springs suggest that the allowed values of energy are effectively continuous. Part of the subtlety of Planck's hypothesis is that Planck's constant has a value of approximately 6.626 times 10 to the negative 34th joules times seconds. Thus, in short, any explanations of phenomena which his hypothesis purports would be consistent in the limit with classical mechanics, which is correct in the region of such observations. A sketch of a derivation of Planck's distribution of energy now follows. This derivation is motivated by the objectives of determining the probability that an oscillator has an energy corresponding to its nth allowed value, and that when n is very large, the discrete character of the energy is unimportant as consistent in the limit with classical mechanics. To enforce the agreement with classical results in the limit, choose the same function of the energy as in the classical theory, that is, e to the negative capital E over kappa times capital T. The probability for a given energy, E sub n equals nhv, is then capital W in terms of n, then times e to the negative capital E sub n over kappa times capital T, which is equal to e to the negative nhv over kappa times capital T. Next, use a formula for the geometric series, namely 1 over the denominator of 1 minus x, which is equal to the sum from n equals 0 to infinity of x to the n, to write a normalization of the previous expression as W of n equals a fraction with a numerator of e to the negative nhv over kappa times capital T all over a sum over n from 0 to infinity of e to the negative nhv over kappa times capital T, then times the quantity 1 minus e to the negative hv over kappa times capital T. Thus, the mean energy is capital E over bar equals the sum over n from 0 to infinity of capital E sub n, then times W of n, which is equal to the quantity 1 minus e to the negative hv over kappa times capital T closed quantity, then times the sum over n from 0 to infinity of e to the negative nhv over kappa times capital T, then times nhv, which is equal to h times v times the quantity 1 minus e to the negative hv over kappa times capital T closed quantity, then times the sum over n from 0 to infinity of n times e to the negative nhv over kappa times capital T. Next, use the following relation to evaluate this sum, namely the sum over n from 0 to infinity of n times e to the negative n alpha equals negative d alpha of the sum from 0 to infinity of e to the negative n alpha equals negative d alpha of 1 over the quantity 1 minus e to the negative alpha, which is equal to a fraction with a numerator of e to the negative alpha over a denominator of the square of the quantity 1 minus e to the negative alpha. Thus, the mean energy relation is capital E over bar equals a fraction with a numerator of h times v times e to the negative hv over kappa times capital T all over a denominator of 1 minus e to the negative hv over kappa times capital T. Next, multiplying by delta capital N yields the Planck distribution capital U in terms of lowercase v equals 8 pi times capital V over c cubed, then times h times lowercase v cubed times the fraction with the numerator of e to the negative hv over kappa times capital T all over a denominator of 1 minus e to the negative hv over kappa times capital T. The exponentials in the Planck distribution can be expanded for small values of hv over kappa times capital T, and the first terms which dominate the outcome of the sum yield capital E over bar equals kappa times capital T. This is congruent with the classical result and is in agreement with the correctness of the Rayleigh-Jeans Law for small values of hv over kappa times capital T. For large hv over kappa times capital T, then capital E over bar tends to hv times e to the hv over kappa times capital T, which leads to Wien's approximation. Between these small and large limits, such as in the visible spectrum of wavelengths, Planck's distribution is in excellent agreement with experiment at all temperatures. The interpretation of Planck's hypothesis further asserts that the decrease in mean energy of the high-frequency oscillators arises because bringing them to an excited state, which is rare, requires a great amount of energy. Lowering the frequency lowercase v or raising the temperature capital T makes it more likely that the oscillator will gain a quanta of energy. If the oscillator is excited to a high quantum number n, its behavior will be essentially classical because the basic unit of energy, h times v, is considerably less than the mean available energy, kappa times capital T. Recall that the initial classical derivation relied on the fact that the black body spectrum is independent of the materials of which the walls are composed. Planck did not begin from this notion. Rather, he assumed that the cavity radiation was in equilibrium with material oscillators in the walls of the container, and that these material oscillators could give up or absorb radiant energy only in quanta according to capital E equals n times h times lowercase v. This step is almost imperative to explain the black body material independence of the cavity radiation. If any radiation were present in energies other than quanta of E equals hv, it could not, by hypothesis, interact with matter and therefore would not be detectable. Conversely, it must be the case that all matter, and not only harmonic oscillators, can absorb or emit radiation in integer quanta of energy hv. Planck's hypothesis is thus equivalent to the statement that all radiation oscillators have their energies restricted to capital E equals n times h times lowercase v. The scope of Planck's starting assumption that the material oscillators in the walls of the black body could give up or absorb radiant energy only in quanta according to capital E equals n times h times lowercase v can be further assessed by considering the specific heats of solids. Specific heat capacity of a substance is the amount of heat that must be added to 1 unit of mass of the substance in order to cause an increase in 1 unit of temperature. Before the advent of Planck's hypothesis, French physicists Pierre, Dulong, and Dulong-Petit proposed a thermodynamic law stating that the heat capacity of a mole of many elementary solids with relatively simple crystal structure at temperatures far from absolute zero is about 3 times capital R, where capital R is the universal gas constant. This is explained in terms of lattice vibrations in the solid. Each atom in a crystal, for example, is in equilibrium when it is in its proper lattice position, and disturbances result in the atom oscillating about the equilibrium position with approximately simple harmonic motion for small oscillations. Each atom can thus be approximated as an independent one-dimensional harmonic oscillator with one frequency lowercase v and possessing energy kappa times capital T, which therefore contributes kappa to the specific heat per atom. Note that the proportionality factor 3 times capital R from the ideal gas constant and kappa are physically the same but scaled for different sample sizes. Capital R is for 1 mole of substance, while kappa is for 1 individual particle. In this case, specifically, 3 times the ideal gas constant capital R is approximately 24.942 joules per kelvins per moles, and the Boltzmann constant here specifically is 1.38 times 10 to the negative 23rd joules per Kelvin. Experimental evidence, however, shows that the specific heat approaches zero, absolute zero, before rising asymptotically to the specific heat capacity ascribed by the Dulong-Petit law. This demonstrates a failure of the classical Dulong-Petit law and a shortcoming of the equal partition theorem at cryogenic temperatures. Einstein would proceed to apply Planck's hypothesis to this problem in his paper published in November of 1906, Planck's theory of radiation and the theory of specific heat. Einstein's proposal in this paper was that the specific heat capacity in this cryogenic region could be explained by assuming that the molecular oscillators are quantized according to Planck's relation capital E equals n times h times lowercase v. Thus, the material oscillators have only one frequency, the characteristic frequency of the substance, as opposed to the radiation oscillators, which can have all possible frequencies. Consider a solid of capital N atoms, which is equivalent to 3 times capital N independent, identical, one-dimensional quantum harmonic oscillators. Then, the mean energy per atom is capital E over bar equals a fraction with the numerator of h times lowercase v all over a denominator of E with an exponent of hv over kappa times capital T then minus 1. So the specific heat per oscillator is given by capital C sub capital V equals d capital E over bar d capital T, which is equal to dd capital T of capital E over bar, which is equal to the previously stated fraction hv over a denominator of e to the entire exponent hv over kappa times capital T minus 1. Since dd capital T of e to the hv over kappa times capital T is equal to negative hv over kappa times the square of capital T, then times e to the hv over kappa times capital T. Thus, we have that capital C sub capital V is equal to kappa times a fraction with a numerator of the square of hv over kappa times capital T, then times e to the hv over kappa times capital T, all over a denominator of the square of e to the entire exponent hv over kappa times capital T, then minus 1. Einstein's formula as capital T approaches infinity predicts that the specific heat per molecule, capital C sub capital V, approaches the Boltzmann constant kappa and approaches zero at very low temperatures as h squared times v squared over the denominator kappa times capital T squared, then times e, then times negative hv over kappa times capital T. Einstein's theory is an improvement on the Dulong-Petit law as the first to apply quantization to explain why specific heat drops to zero as the temperature approaches absolute zero. As such, it is a clear demonstration that quantum mechanics can solve the specific heat problem in classical mechanics. Einstein's model of specific heat, in spite of its general agreement with experiment, was not completely accurate at very low temperatures on the order of 10 degrees Kelvin. This discrepancy would be rectified by Peter Debye's model, developed in 1912, by estimating the contribution of a quasi-particle known as a phonon. The oscillations of each atom are actually not independent, but are coupled because of intermolecular forces. Debye's model treats atomic vibrations as collective quantized sound waves from the phonons within a continuous medium. The Debye model accurately predicts that heat capacity vanished on the order of capital T cubed at cryogenic temperatures and obeys the Dulong-Petit model at high temperatures. Coupled oscillations can be described by considering a one-dimensional string of particles. A similar treatment can be given in 3 dimensions to therefore describe the propagation of sound waves through a crystal. Suppose that each particle interacts only with its 2 nearest neighbors. Waves can then be shown to propagate through this system resembling waves propagating through a chain, except that the waves are both longitudinal and transverse in this proxy crystal system, whereas the waves in a chain are only transverse. For wavelengths that are large compared to the distance between particles, the wave propagation is marginally different from that in a continuous string. However, as the length of the waves approaches the mean distance between particles or smaller, propagation becomes impossible. In such a one-dimensional string of particles, let the equilibrium distance between particles be denoted lowercase a. Suppose the force on the nth particle is given by F sub n equals negative m times the square of omega sub 0, then times the larger outer quantity, inner quantity, x sub n minus x sub n minus 1 close quantity plus quantity x sub n minus x sub n plus 1 close all quantities, which is then equal to m times x double dot sub n, where x sub n is the deviation of the nth particle from its equilibrium position. Compute a solution of the form x sub n equals capital A sub n times e to the I omega t, and show that it can be chosen that capital A sub n equals e to the I alpha n, where alpha is a suitable constant whose relationship to omega is obtained by the solution being sought. From Newton's second law, m times x double dot sub n equals f sub n. Thus, x double dot sub n is equal to the negative of the square of omega sub 0 times larger outer quantity, then quantity x sub n minus x sub n minus 1 close quantity plus quantity x sub n minus x sub n plus 1 close all quantities, which is then equal to the negative of the square of omega sub 0, then times the quantity 2 times x sub n minus x sub n minus 1 minus x sub n plus 1 close quantity. From x sub n being equal to capital A sub n times e to the I omega t, then x double dot sub n is equal to negative omega squared times capital A sub n times e to the I omega t. Substituting this into the result from Newton's second law and dividing by e to the I omega t yields negative omega squared times capital A sub n equals the negative of the square of omega sub 0, then times the quantity 2 times capital A sub n minus capital A sub n minus 1 minus capital A sub n plus 1 close quantity. The choice of capital A sub n equal to e to the I alpha n implies that capital A sub n plus or minus 1 is equal to e to the I alpha times the quantity n plus or minus 1 close quantity, which is equal to e to the plus or minus I alpha then times e to the I alpha n. Therefore, negative omega squared times e to the I alpha n is equal to negative of the square of omega sub 0 then times the quantity 2 times e to the I alpha n minus minus e to the negative I alpha, then times e to the I alpha n, minus e to the I alpha, then times e to the I alpha n closed quantity, which is equal to the negative of the square of omega sub 0, then times e to the I alpha n, then times the quantity 2 minus e to the negative I alpha minus e to the I alpha closed quantity. Hence, omega squared is equal to the square of omega sub 0, then times the quantity 2 minus e to the I alpha minus e to the negative I alpha closed quantity, which is equal to the square of omega sub 0, then times the quantity 2 minus 2 times cosine of alpha closed quantity, and thus factoring out the 2 leads to 2 times the square of omega sub 0, then times the quantity 1 minus cosine alpha closed quantity. Using the trigonometric identity, 1 minus cosine alpha equals 2 times sine squared of alpha over 2 yields omega squared equals 4 times the square of omega sub 0, then times sine squared of alpha over 2, and omega equals 2 times omega sub 0 times the magnitude of the sine of alpha over 2. Therefore, alpha is determined by omega up to sine and periodicity in alpha. Next, show that for low frequencies the oscillations resemble sine waves, and that omega is approximately 2 pi times lowercase v over lambda, or equivalently, omega is approximately lowercase v sub s times k, where lowercase v sub s is equal to omega sub 0 times a, is the speed of sound in the system. In the low frequency limit, omega is small, therefore the magnitude of the sine of alpha over 2 is small, therefore alpha is small, therefore the sine of alpha over 2 is approximately alpha over 2. Therefore, omega is approximately 2 times omega sub 0, then times the magnitude of alpha over 2, which is equal to omega sub 0 times the magnitude of alpha. Next, consider the wave number. The spatial period of capital A sub n is equal to e to the I alpha n in the discrete index n. The spatial period of capital A sub n equal to e to the I alpha n in the discrete index n corresponds to a spatial coordinate x equal to NA. So the phase is alpha times n, which is equal to the quantity alpha over a closed quantity times the quantity n times a closed quantity, which is equal to k times x, with k equal to alpha over a. Therefore, alpha equals k times a, and omega is approximately omega sub 0 times the magnitude of k times a. Then, this is equal to lowercase v sub s times the magnitude of k, and so lowercase v sub s is equal to omega sub 0 then times a. The dispersion of sound waves is given by omega being equal to lowercase v sub s times k, and lowercase v sub s equal to omega sub 0 times a is the speed of sound. In terms of wavelength, lambda equals 2 pi over k, and frequency lowercase v equals omega over 2 pi. Omega is approximately equal to 2 pi times lowercase v, and k equals 2 pi over lambda. So omega is approximately equal to lowercase v sub s times 2 pi over lambda. That is, v is approximately lowercase v sub s over lambda. Finally, show that there is a maximum possible frequency, from omega being equal to 2 times omega sub 0 times the magnitude of the sine of alpha over 2. The maximum occurs when the magnitude of sine of alpha over 2 is equal to 1. That is, alpha over 2 equals positive or negative pi over 2, so alpha equals positive or negative pi. Therefore, the maximum possible frequency is equal to 2 times omega sub 0. For alpha equal to pi, then capital A sub n equals e to the I pi n, which is equal to negative 1 to the n, and so adjacent masses oscillate out of phase. This is the shortest wavelength supported by the discrete lattice, that is, a wavelength of lambda equals 2 times lowercase a, and there is no propagation for omega being greater than 2 times omega sub 0. As was done with the electromagnetic field, the amplitudes of the possible sound waves can be adopted as coordinates to describe the state of the system. Since these coordinates oscillate harmonically with time, the energy of the associated oscillators must be quantized. Only a finite number of wavelengths is permissible, and the relation between frequency and wavelength becomes more complex as wavelengths comparable to interatomic spacing are approached. These facts must be taken into account in computing the energy. In all, these factors suggest that the quantum hypothesis leads to excellent general agreement with experimental specific heats at all temperatures. Furthermore, in addition to the quantization of electromagnetic energy, there is evidence for the existence of the quantization of sound energy. The conclusion is therefore that all systems which oscillate harmonically are quantized with capital E equals n times h times lowercase v, whether these systems are material oscillators, sine waves, or electromagnetic waves. The assumption that all systems can interact with each other implies that the quantization of any one type of harmonic oscillator requires a similar quantization of all other types. Without this unity being experimentally evident, quantum theory would need to be abandoned or at least fundamentally modified.